Hello students, in today's video I am going to discuss the reactions of haloarenes with you. So without wasting any time, let's begin the video and explore reactions of haloarenes. Reactions of haloarenes. First are nucleophilic substitution. Aryl halides are externally less reactive towards nucleophilic substitution reactions due to the following reasons. Number one, resonance effect. In haloarenes, the electron pairs on halogen atom are in conjugation with pi electrons of the ring, and the following, according to figure, resonating structures are possible. Carbon-chlorine bond acquires a partial double bond character due to resonance. As a result, the bond cleavage in haloarenes is difficult than haloalkane, and therefore they are less reactive towards nucleophilic substitution reaction. Number two is difference in hybridization of carbon atom in carbon halogen bond. In haloalkane, the carbon atom attached to halogen is sp3 hybridized, while in case of haloarene, the carbon atom attached to halogen is sp2 hybridized. The sp2 hybridized carbon with a greater S character is more electronegative and can hold the electron pair of C single bond X bond more tightly than sp3 hybridized carbon in haloalkane with less S character. Thus, carbon-chlorine bond length in haloalkane is 177 picometer, while in haloarene is 169 picometer. Since it is difficult to break a shorter bond than a longer bond, therefore haloarenes are less reactive than haloalkanes towards nucleophilic substitution reaction. And number three is instability of phenyl cation. In case of haloarenes, the phenyl cation formed as a result of self-ionization will not be stabilized by resonance, and therefore SN1 mechanism is ruled out. Number four is because of the possible repulsion. It is less likely for the electron-rich nucleophile to approach electron-rich arenes. Replacement by hydroxyl group. Chlorobenzene can be converted into phenol by heating in aqueous sodium hydroxide solution at a temperature 623 Kelvin and a pressure of 300 atmospheres. The presence of an electron withdrawing group like NO2 at ortho and para positions increases the reactivity of haloarenes. The effect is pronounced when NO2 group is introduced at ortho and para positions. However, no effect on reactivity of haloarenes is observed by the presence of electron withdrawing group at meta position. Mechanism of the reaction is as depicted. A simple question is, can you think why does NO2 group show its effect only at ortho and para position and not at meta position? Answer is very simple. As shown, the presence of nitro group at ortho and para position withdraws the electron density from the benzene ring and thus facilitates the attack of the nucleophile on haloarene. The carboanion thus formed is stabilized through resonance. The negative charge appeared at ortho and para positions with respect to the halogen substituent is stabilized by NO2 group, while in case of meta-nitrobenzene, none of the resonating structures bear the negative charge on carbon atom bearing the NO2 group. Therefore, the presence of nitro group at meta position does not stabilize the negative charged and no effect on reactivity is observed by the presence of NO2 group at meta position. And next, second is electrophilic substitution reactions. Haloarenes undergo the usual electrophilic reactions of the benzene ring such as halogenation, nitration, sulphonation and Friedel-Crafts reactions. Halogen atoms, besides being slightly deactivating, is ortho para directing. Therefore, further substitution occurs at ortho and para positions with respect to the halogen atom. The ortho-para directing influence of halogen atom can be easily understood if we consider the resonating structures of the halobenzene. Due to resonance, the electron density increases more at ortho and para position than at meta positions. Further, the halogen atom, because of its minus I effect, has some tendency to withdraw electrons from the benzene ring. As a result, the ring gets somewhat deactivated as compared to benzene, and hence the electrophilic substitution reactions in haloarenes occur slowly and require more drastic conditions as compared to those in benzene. Halogenation reaction of chlorobenzene, that is addition of halogen such as chlorine or bromine in presence of FeCl3 or FeBr3 catalyst. Nitration reaction of chlorobenzene, addition of nitro group at ortho and para position with concentrate H2SO4 and HNO3 nitriding agents. And sulphonation reaction of chlorobenzene, that is addition of sulfonic acid at ortho and para position in the or with the help of concentrated fuming sulfuric acid. And next is Friedel-Crafts reaction of chlorobenzene. It is a addition of alkyl or acyl group in presence of anhydrous AlCl3. Now next is an example. Although chlorine is an electron withdrawing group, it is ortho para directing in electrophilic aromatic substitution reactions. Why? And the answer is very simple. Chlorine withdraws electrons through inductive effect and releases electrons through resonance. Through inductive effect, chlorine destabilizes the intermediate carbocation formed during the electrophilic substitution. Through resonance, halogen tend to stabilize the carbocation, and the effect is more pronounced at ortho and para positions. The inductive effect is stronger than resonance and causes net electron withdrawal and thus causes net deactivation. The resonance effect tends to oppose the inductive effect for the attack at ortho and para positions, and hence makes the deactivation less for ortho and para attack. Reactivity is thus controlled by the stronger inductive effect, and orientation is controlled by resonance effect. And third is reactions with metals. In this, first is Wurtz-Fittig reaction. A mixture of an alkyl halide and aryl halide gives an alkyl arene when treated with sodium in dry ether and is called Wurtz-Fittig reaction. And next is Fittig reaction. Aryl halides also gives analogous compounds when treated with sodium in dry ether in which two aryl groups are joined together. It is called Fittig reaction. Students, through today's video, you have learned reactions of haloarenes. I hope you enjoyed the video. So to keep receiving more videos from me, please like and subscribe to the channel and share it as widely as possible. That's all for now. See you in the next video.